solve this multivariable limit on the screen. Yesterday we also solved a multivariable limit, and I told you that you can use much the same techniques as you would use for a univariate limit, which is largely true, but there are cases where it helps to first check whether the limit exists on certain parts, so that you at least know what you're trying to prove, and so that if it doesn't exist, it's much easier to notice from the get-go than to go on trying to prove something that doesn't actually exist. So before I go ahead and show you the solution for this particular limit, I wanted to point out that there are 12 days left in the Maths Countdown series. So you're rapidly approaching the end of the series, and I encourage you to stick around until the end. Okay, so if we look at this limit here, it would be very difficult to now go ahead and try and prove this limit, or to come to some sort of verdict, or to either conclude that it exists or doesn't exist by simply trying to evaluate it, manipulate it, or anything along those lines. So what we should actually do when we have multivariable limits is to test it on certain parts, because for multivariable limits, it means that this function is existing in 3D space, because it's a function of multiple variables. And if it's existing in 3D space, then in order for the limit to exist, we have to approach it from any direction and still get the same answer. So for single variable limits, such as the limit of a function of x, then we approach it from the left and the right, and if both of those limits are equal, then we say that the limit exists. But for multivariable limits, it's different in the sense that we have to have this limit existing from all approaches. It must be the same from whatever angle or whatever line you approach this limit on. So it's good to check a few first before you go ahead and try and solve it, because you might end up trying to solve something that's very difficult to solve, like this limit on screen. So we are going to check along the x-axis, or the y is equal to 0 line. Okay, so along the x-axis, our y is 0, so we can now substitute in 0. So we now have the limit as x approaches 0, because our y is going to be 0 everywhere in here, so we're not going to have y in this function anymore. So we're going to have x squared plus 0 over 0 plus x, and I'm sure you can see that those zeros come from those two y's. Okay, so then what we essentially have is the limit as x approaches 0, and then that x cancels with one of these x's over here, and we're just doing the limit as x approaches 0 of x. And we see then that that is equal to 0. Okay, now we have to see if this limit is the same when we check it along another path. So let's check it along y is equal to x. Now you may be asking, why did I choose y is equal to x, and why did I choose y is equal to 0 or the x-axis? And it doesn't really matter which one you choose or whatever you choose to test it along, because it should be equal on all of the tests that you do. So no matter what line you tested along, it should be equal. So I could have tested along y is equal to x squared, and I should get the same answer. But the reason why I'm doing it on y is equal to x and y is equal to 0 is because it's more convenient and it's easier to do it. So just look for things that are easy or convenient to solve the limit, and then do it along those lines. But you should also know that no matter what you choose to test it along, it should give you the same answer. It just depends on what's more difficult or what's easier. So if we're testing it on y is equal to x, then every time we see a y, we're going to substitute in an x, or every time we saw an x, we'd substitute in a y. So let's do it for substituting in our x's for y. So we then have the limit as x approaches 0 of x squared plus x over, because I substitute an x for that y. Now I'm going to substitute an x for this y squared, so I have x squared plus x. And then you'll notice that those cancel, it's equal to 1, so this limit is then equal to 1. But now our limit along the x-axis is different to our limit along the y is equal to x line. So we can therefore conclude that the limit does not exist. And it doesn't exist for the sole reason that these limits are not equal to each other. It's very similar to if you were testing a limit of a univariate function from the right-hand side and the left-hand side, and those weren't equal. Then you'd say that that limit doesn't exist. So in this case, the limit doesn't exist because when we tested it along the x-axis and along the y is equal to x line, we got different answers for our limit. So it can't exist because they're not the same value. Okay, so I hope you found this video useful and interesting. And if you have any questions regarding the content I've covered today, please don't hesitate to leave your queries in the comment section below. Thank you for watching.